All right, those little pages I gave you, they're not as colorful as this, but they're saying the same thing. On one side, it's saying, well, what rule do I use? Because what's confusing about this probability stuff is, number one, what rule do I use? And so if you follow the logic here, it says, you find in just one event's probability. If so, then you're going to go along the top branch. And most of the time it's going to be the outcomes are equally likely, and so you're going to do this fraction, the number of ways to do an event divided by the total number of ways. That thing, that classical kind of probability. Notice one of the choices here is, if not all else fails, use subjective probability. What's that? Well, that's a number you just make up based on your experience. Bless you.
Wait, what?
It's something based on your experience, what you've observed. You can say, well, subjectively, I think the probability is not very likely that this is going to happen.
Oh, okay.
It's just based on you. That is a choice. And the more interesting ones are the ones that you're finding compound events. So you're taking this bottom path. And so look at the first question. Is it an or thing or an and thing? If it's an or thing, your first thought ought to be, well, that means the addition rule, are these two things disjoint? If so, you use, one version of the addition rule. If not, you use the other version. If it's an and thing, your first question ought to be, are they independent? Because you got two flavors of the multiply rule. And then down here, this at least one, don't forget about it. It gets important on some problems. Anytime you see that magic phrase, at least one, you need to think, okay, I know what that means. At least one is the opposite of none. Then on the flip side, we've got, how am I going to count this? That's what we talked about yesterday. And there's a variety of ways to do that. We talked about the multiplication rule, combinations, permutations when the things are not distinct. Yes, ma'am.
Was yesterday's video up?
Mm-hmm. Okay, so that's that little page. You don't get to use it on the quiz, but it's a good study aid, I hope. And it's in the book. So I thought we'd just work some problems. All right, starting with this one. 10 girls, but only 5 can be on the field at any given time. 4 fielders and a goalie. How many starting lineups are possible if all players are selected without regard to position played? Okay, so we're looking at that. Does it seem like order makes a difference there? I don't think so either. So, thinking combination. So I've got 10 girls chosen 5 at a time. What's that equal? All right, so we're getting 252, ma'am.
How do you know the order of the screen?
You have to just get it from the context of the problem. It's on this one, it said without regard to position played. That's a good question because that's pretty important, right? So that was A. B, how many starting lineups are possible if either Peyton or Jordan must play goalie? Okay, so I would write it out like this. Here's a goalie. All the others just there. How many choices do I have for goalie? 2. Now the order doesn't matter. So for these 4 that are remaining, combination, right? So I'm choosing How many girls do I have left?
8, 9.
9. Once the goalie's chosen, I've got 9 girls left. So that would be 9, combination, choose 4. What do we get there?
So if order doesn't matter, it's always combination.
Wait,
Right?
9 times out of 100. I hate saying always.
I was writing down A, and now I'm lost.
Okay, so for goalie, we got 2 choices, either Peyton or Jordan.
Okay.
And then I'm going to multiply that times, once I've got the goalie, then I've got 9 girls to choose from to get 4 out of that group. What's 9 combination 4?
1.6.
How many?
1.6.
Thank you. So we're back to 2 times 126 is 252 again. So that didn't really change anything. So there's 252 ways that either Peyton or Jordan could be goalie, and then we get the rest of the girls. If the order had mattered there, we'd have a whole different problem. This kind, I think you're going to find are the toughest ones. So take a second and read it. These can drive you crazy if you don't have a plan. So here's what I suggest. When you're reading this, jot down how many are bad and how many are good. And then you start trying to figure this out. Now, it's asking for a probability of accepting the shipment. Since it's a probability, I need a numerator and a denominator. So I'm reading this, I'm going to pull 4 modems out and test them. If all 4 work, we're going to accept the shipment. So I'm looking for the the probability of all 4 working, right? Now then, does the order matter?
No.
Now I'm just getting a group of 4. How many am I choosing those 4 from? Here's the trick. One of them. How many good ones are there? So the only way I'm going to get 4 is by choosing from those 17. Now, I'm not separating the 17 out. I'm just saying there's only 17 good ones that I can get 4 good ones from. The order doesn't matter, so I'm going to say 17, combination 4. But we're not done. I'm also going to say times, how many bad ones are there? So I'm going to say 3, and this might not make sense right now. How many am I choosing the bad ones? I've already got 4 from the good ones. 0. And you're looking at me like, okay, why are we doing that? There's a reason.
What's the reason?
If you put in your calculator 3 combination 0, you're going to get the number 1. So if it doesn't affect this, why are we doing it? Because sometimes that won't be 0. So that's my numerator. What's my denominator? I'm choosing 4 out of the whole bunch. That's the total number of ways I could do it. So how many am I choosing from? 20. Combination 4. Okay, so let's put some numbers with this. Okay, when I work it out, I'm getting 2380. That's my 17 combination 4. The 1 is from the 3 combination none. And 20 combination 4 is giving me 4845. Now, that's my answer. If the problem says make it a reduced fraction, then I can have the calculator do that for me. Or I can do it by hand. I know that's going to reduce because The top number ends in 0 and the bottom one ends in 5. So I know I can reduce it at least by 5. But when I reduce it on the calculator, what am I going to get?
28 over 57.
Say again?
28 over 57.
28?
Yes.
Thank you. That's my probability of drawing 4 good ones. Let me show you why I want to do that 3 combination 0 thing. What if it was, we're making up a totally different problem. What if it was the probability of getting 2 good and 2 bad? Now my denominator is going to stay the same. It's going to be choosing 4 out of 20, and the order doesn't matter. But now, for the good ones, I've got what? 17, choose how many? 2 times 3, 2. Let's see how that changes anything. So when we do it this way, look what I'm getting. Changes things drastically. So just get used to putting that added little thing out there, even if you're not choosing any. On this kind of problem, it'll save you. And anybody want to reduce 408 over 4845, or will it reduce?
8 over 95?
It's what?
8 over 95?
Thank you. Totally different. Let's stop there and see if we got questions. Slightly different problem. This is based on the Titanic. Now, the way they did this table, they said if you're male, it means adult male. If you're female, adult female. Child could be male or female, right? Just means not an adult. Okay, so what's the probability for A? What's the probability if I just choose one passenger at random that they survived? Well, I look at the survived row here. I'll look at the total. And they were nice enough to total these up for us. So the probability of surviving is what? 711 out of 2224. I could leave that as a fraction. I'm kind of thinking that one's not going to reduce. I can make it a decimal. So you got to read the question and say, do they want a reduced fraction or a decimal? So looking at that, only about a third of the people survived. What a great time. Okay, look at the next question. What's the probability that the passenger was female? Well, I look at females. I look at the total. And I've got 425 out of 2224. Again, reduce it if you can. Make it a decimal, depending on what the problem asks you to do. Am I going too fast? What's the probability that the passenger was female or a child? Now we need to stop a second and think about this. I'm seeing the word or, so my brain automatically starts thinking, what rule? Addition, good. My next question is, are female and child, are they disjoint the way they did it? Yeah. Female means adult female, child means not an adult. So I could have female children, but they count as a child, not as a female. Okay, that's how they did this table. So you have to know how they did it. So are they disjoint? Yeah. That means I can just add their probabilities, right? Because it's the addition rule. So the probability of female, we said, was 425 out of 2224. Plus, what's the probability of a child? 109 out of 2224. So that's going to equal what, 534 out of 2234, 2224. Reduce, decimal, whatever. What's the probability that the passenger was female and survived? I'm seeing the word and. Multiplication, good. Are they independents?
Yes. No. I don't know.
We can't assume they are.
Because they're female spiders.
Uh-huh.
There's two.
There's some overlap there. The overlap doesn't matter. The overlap doesn't matter, but the independence does. We're going to treat it as though they weren't independent. Nothing told us they're independent. So I'm going to say, okay, the probability of female times, and here's where that conditional probability comes in, the probability of survive given that we picked a female. So what's the probability of female? Well, it's still 425 out of 2224 times, now then I've got to say, all right, given that I got a female, what's the probability she survived? So I narrow my sample space down to just females, right? Given that I got a female, so I'm just looking at this. What's the probability she survived? 316 out of 425. Stop there and think about that. Out of the 425 females, 316 survived. This is a conditional probability. So I'm using the general multiply rule. It says you got to take into account that maybe these aren't independent. Unless you're told they are, you can't assume that they are. Okay, so I multiply those together. What am I getting? $425 times 316. Somebody help me out.
134,300.
Thank you. Over 2224 times 425. Oh, wait. Hold on. Scratch that. I appreciate the help, but I'm looking at this and I can go, oh, 425 there, 425 there. So what's 316 divided by 2224? Well, I can leave it as a fraction. I can leave it 316 over 2224. Let's do that.
9 over 556.
Thank you. 79 over, how big?
556.
Thanks. If I wanted a decimal, I could divide that out. Would you say females had a better chance of survival than males? Yeah. About that same number of males survived. Compare how many died. Great to be a guy on the Titanic. No.
Okay.
All right. So, what's the probability the passenger was female or survived? I'm seeing the word or. Again, possibly a description of Rose, but let's keep going. I'm seeing or. Addition. Or the events female and survivor, are they disjoint? No, they're not. So I've got to use the general addition rule. So I've got probability of female plus the probability of survived minus the probability of both. Because there's overlap. All right, so I've got still 425 out of 2224. What's the probability of survivor? Well, we did that. That's the first thing, 711 out of 2224. Minus the probability of both. Well, let's see. Female and survival. There we go. So minus 316 out of 2224. So however those add up, what's that going to be? 1136 minus 316. So 820 over 2224, reducible, yeah, they're both even numbers, so I know I can reduce it at least some. And that's how you answer those. That table, you just got to know how to use the table. And they were nice enough to total these up for us. Okay, let's look at Sean planning his college and taking the SAT test. He's allowed to select 3 schools to send his scores to. There's 12 colleges he's considering. And how many different ways could he fill out the report form?
That's 12, and that baby, and then 3.
First of all, okay, 12. Does the order matter that he puts these colleges on the form? No. So I've got 12 combination 3. Again, there's that intuitive word again. That doesn't seem to make sense to our brains, that he could do that. If we had a list of all the colleges, we could, on a big piece of paper, list all of those. I don't want to. So let's say 3 of the colleges were UT, NTSU, and Harvard. What's the probability he would get that list right there? Good. Be 1 out of 220. That's what he would put. Because there's only one way that I can do this where the order doesn't matter. All right, let's look at another one here. NHS. We're going to draw one student's name at random. What's the probability that we got a junior? What didn't they do for us here?
Totals.
Yep. Let's total them up and see what we get. So junior, I've got 112 out of 449. Again, just using the table. There's our answer. Possibly reducible, maybe not. But there's our answer. What's the probability that this student we drew is a senior, given that we know we got somebody in NHS? Again, they didn't total this for us. So what do we got? 87? So we're saying the probability that we got a senior, given that the person we drew is in National Honor Society. So what am I doing? I'm just concentrating on this column right here. So 37 out of 87. What's the probability I got a freshman, given that I drew somebody in the National Honor Society? Ain't happening. Not at this high school. Can freshmen even get in? Okay. Okay. Todd's going to get a sequence of exercises for his exercise routine. And he thinks the sequence of exercises can affect his overall performance. Now, just intuitively, what's that saying? Does the order matter or not?
Yeah.
Yeah. All right, so the order matters, so I'm going to leave combinations out of it. He has 12 exercises to select from, but only has enough time to do 9. So I'm thinking permutations. So I've got 12 permutations where I'm choosing 9. What does that equal? That number does not make sense to my mind. That with only 12 exercises and only doing 9 of them, there's that many ways you could arrange them.
But, so just because, like, the order matters, you just use a different calculator?
You use this one. That P stands for permutation. The order matters.
But, like,
What if we did this, y'all?
why?
2, 4, 5, 6, 7, 8,
How does
9.
it know what orders matter?
You tell it. If you put permutation, you, the human, is saying the order matters.
Yeah, but how does it know, like, which orders are good and which orders are bad?
That's a good question. If you look at your formula pages, it actually gives you the formula for permutations if you want to calculate it. Let's do this. I put 9 blanks down here. 1, 2, 3, 4, 5, 6, 7, 8, 9. For his exercise routine, how many choices do we have for the first exercise? Once that one's chosen, how many for the next one? And then 10, and then 9, 8, 7, 6, 5, 4. Let's multiply all those together. I could have just worked this problem doing it the multiplication rule, right? This is why it's so big. We're multiplying all those numbers together. Because, okay, look at it like this. Just take the first 2. I've got 12 choices for the first exercise. For each one of those choices, I've got 11 choices for the second exercise. Yes, ma'am.
So for the, like, when you put it in the calculator, like the NPR thing, is that just saying, like, it's the exclamation mark, but only this number of times? Is that basically what it's doing?
If you'll get your formula pages out, just real quick, if you don't mind.
I know, I was just trying to.
What's the formula for this? The formula for NPR is what?
N exclamation point.
So n factorial over
N minus R.
factorial.
Oh, yeah.
Okay, so that means it'd be 12 factorial, which we just figured out. No, we didn't. We left out 3, 2, 1. Over, what's 12 take away 9?
3.
If you put in your calculator 12 factorial, it's going to be a huge number, divided by 3 factorial, which is just 6. You're going to get this 79,833,000, blah, blah, blah. And you'll reach a, that's why.
Yeah, that's what I, sorry.
Yeah. You'll reach a point, not a whole lot bigger than that, that if you try and get the factorial of the number, your calculator just tells you to go away because it can't do it. All right, let's look at, these all came out of the end of the section. This Genesis has 2 engine types, 2 vehicle styles, 3 option packages, 8 exterior color choices, and 2 interior color choices. How many different Genesises can we put together?
Oh, no. None. Yeah.
This is just the multiply rule, isn't it?
Yeah.
How many blanks do I have? I've got engine type,
Times 3 times 8.
I've got vehicle style, I've got option, I've got exterior, I've got interior. So there's 5 different things here. For the engine type, I've got 2 choices. Vehicle style 2, 3 option, 8 exterior, 2 interior. Just multiply.
Oh,
So 2 times 2 times 2 is 64 times, I'm sorry, it's 8 times 8, 64 times 3,
192.
192. Just the plain old multiply rule. That's the kind you hope to see on a quiz. All right, I'm going to draw 3 cards from a standard 52 card deck. What's the probability all 3 are aces? That means ace and ace and ace. Now, I'm not putting the cards back. So the probability of 3 aces, what's the probability of first one being an ace?
4 out of 52.
Okay. Now then, once that card's drawn, given that I got an ace on the first one, this is conditional probability, right? Given that I got an ace on the first one, what's the probability of getting an ace on the second one? Exactly right. Given that I got an ace on the first 2, what's the probability of getting an ace on the third one? Good. So I've got 24 out of 52 times 51 times 50, whatever that comes out to be. Reducible? Yeah. Let's not take the time to do it. Pretty easy to reduce. Now then, look at 23 here. How many different vertical arrangements for 10 flags if there's 4 white, 3 blue, 2 green, and 1 red? When you got this kind of thing, imagine seeing those 10 flags. And let's say, just for the sake of argument, that it went white, blue, green, red, white, white, blue, green. What have I left out? 1, 2, 3, 4, 5, 6, 7, 8. We've got another white one. We've got another blue one. Let's suppose it just looked just like that. If I swapped this blue one for this blue one, are you going to be able to go, oh, you swapped flags? No. These are not distinct. One blue flag is just like the other blue flags. When you got this situation, you've got that different kind of permutation. This is the permutation of non-distinct things. So what do we do there? We use this formula, also in your formula pages. So how many things are there? 10. So let's just start there. So I've got 10 factorial. I don't want to write the formula out because it can be confusing. So then I just take each color and make it factorial. So I've got white ones, 4 factorial. 3 blue, so that's 3 factorial. 2 green. And 1 red. So on the bottom, you can put all those in the calculator, but it's going to take you a minute to put all those factorial symbols because you got to go back to do it. I'm just looking at it like this. You don't have to do it this way. I know 4 factorial is 4 times 3 times 2 times 1. That's 24. 3 factorial is 6, 3, 2, 1. 2 factorial is 2. 1 factorial is 1. So I've got, 12 times 24 on the bottom without having to put all those factorial things in? So whatever 12 times 24 is, let's see. Okay, I've got 288, and I know 10 factorial is 3 million something. Anybody figure that one out? All right, with some help, we figured out 3,628,800. And I'm going to divide that by 288, and that's how many different arrangements I could come up with. Now, that's a bunch, but it's a whole lot less than if I said, well, I've got 3 different shades of blue and 4 different shades of white. Then it would be a permutation of just 10 factorial. That'd be 3 million, right? Because I wouldn't be dividing by those others. All right, we're getting there. Ooh, another one of these. So we've got a case of 12 bottles of wine, 5 are Merlot, so we make note of that, and 7 are Cabernet. The bottles all look alike, and so each one has an equal probability of being chosen. We're going to pick 3 of them. First of all, does the order matter?
No.
No, we just got 3 bottles of wine. So question A says, what's the probability that all 3 are Merlot? The order doesn't matter. It's a probability. I need a numerator and a denominator. So how do I get 3 Merlot out of 5 when the order doesn't matter? How many am I choosing from of Merlot? Order doesn't matter, so it's a combination. I'm choosing 3. Now then, don't forget, do this. I've got 7 Cabernet. How many am I choosing of them? 0. So I'm going to put, just for the sake of my broken heart, I'm going to put 7 combination 0. Because I know that's going to be 1. 7 things taken 0 at a time. There's only one way I can do that. On the bottom, I've got what? 12 things taken 3 at a time. So from this, we're getting 10 over 220. I can cancel those zeros pretty easy, so I'm getting 1 over 22. That's the probability of getting all 3 Merlots. Then B, the probability of getting 2 Merlots. But that leaves 1 Cabernet. So I've got 5 Merlots to choose from. I'm picking 2 out of those now. Times, I've got 7 Cabernet. I'm picking 1. This is still going to be that on the bottom. Let's see how that changes things. So I get 70 over 220, which is 7 times more likely than what we got up there for A. So I've got 7 over 22. Finally, for C, I've got the probability of all 3 of them are Cabernet. So I've got 7 Cabernet that I'm picking 3 from, times 5 Merlot that I'm picking 0 from over this, which hasn't changed, which is going to give me 35 times 1 over 220. And we could certainly reduce that. Okay, watch out for these kinds of problems. They are tricky. Here's our last one. The Cubs have won 58% of their games that's over a whole season. So we're assuming that sort of percentage is going to continue, and it's important that they're telling us that these games are going to be independent. All right, so A is saying, what's the likelihood that they're going to win 2 games in a row? Well, that means they win the first one and the second one. So that means what? The probability of a win and a win. Since they're independent, I can just multiply those probabilities. So be 0.58 times 0.58, which is the same as 0.58 to the second power, which is 0.3364. So that's going to happen about a third of the time. B is saying, well, what's the probability going to win 7 in a row? So that means what? Win and win and win 7 times. That's going to be 58% to the 7th power, which is 0.0221. Right. Only about 2% of the time are they going to win 7 games in a row. Look at C. What's the probability that they will lose at least 1? There's that magic phrase again, at least 1. So we know that at least 1 is the opposite of none. Think about what we found in B. We found the probability that they won 7 games. Isn't that the same as the probability of losing none of those 7? And the answer is, well, yeah. So I can use this. Let me know if you got some questions.